So this is a joint work with Antoine and Florent from University of Clermont-Ferrand in France, and with Professor Ralph Plassing from Labrie, University of Bordeaux. And thanks to Antoine for most of the slides. So yeah, so let's start with the problem setting. So we have the path cover problem, which is, so what is a path cover? It is a set of paths that cover all vertices of a graph or a diagram. Now, the path cover problem asks, to given a graph or a diagram as input, we want to find the path cover of minimum size. Now, of course, this is a hard problem in general, but it is polynomial time solvable in directed acyclic graphs. And that is kind of the starting point of this work. So, and this polynomial time algorithm is also associated with the famous Dilworth theorem, which says that the minimum size of a chain partition of a finite partially ordered set is equal to the maximum size of an anti-chain of this poset. Yeah. Now, if we simply restate it in terms of graphs, what we have is that the minimum size of a path partition of a transitive directed acyclic graph is equal to the maximum size of an anti-chain of this directed acyclic graph. So what do we mean by an anti-chain? Is a set of it is a set of vertices that are pairwise unreachable in the DAG. Okay, and so you can partition the transitive direct acyclic graph with whose size is equals to the lower bound. Yeah. Now, and for general DAGs, again we can restate it in terms of a path cover. So the minimum size of a path cover of a directed acyclic graph is equal to the maximum size of an anti-chain of this directed acyclic graph. So here we don't have a partition, but a cover. Okay. And what we kind of wondered is, can we have a similar theorem for, let's say, temporal directed acyclic graph? I will define what we mean by that. So, of course, I mean, there is an algorithmic proof for this, and like it has been studied quite a lot. So we want a temporal analog of Dilworth's theorem. So just so that we are all on the same page, temporal, we have the usual notion of a temporal digraph, so that every arc, with each arc, we have a set of time labels. So it has many applications in various areas of DAG. Is basically the global graph, the union of all the arcs over all the timestamps is basically a directed acyclic graph. Okay. Similarly, we have a definition of the temporal trees and so on. And we'll be concerned with strictly increasing time labels of paths. So a temporal path or a directed temporal path is a path or a directed path where the time labels are strictly increasing. Okay, so in this picture, as you see, that these two time labels are same. So this is not something we allow. Now, we say that a temporal path occupies a vertex during the interval t1 to t2 if it reaches it at time t1 and leaves it at time t2. So basically, that's how a path offsets. And similarly, when you have a notion of occupation, you can also define the notion of intersection of two paths. Yeah. So the two paths intersect if they occupy the same vertex during non-disjoint intervals. Otherwise, they are temporally disjoint. So two vertices are temporally connected if there is a temporal path between them. Yeah. And it's a temporal antichain is a set of vertices who are pairwise not temporally connected. Okay. Now, what we hoped, or it would have been very nice if we had a theorem which would say that for all temporal direct acyclic graph, the minimum size of a temporal path partition or cover is equal to the maximum size of a temporal antichain. But unfortunately, such a thing won't exist because there are, let's say, tournaments where temporal tournaments where you don't have this Dilworth property. Okay. So we'll be concerned with two problems. So one is temporal path cover of temporal DAGs, and temporal path partition or temporally disjoint path cover. So in this version, we want to cover all the vertices of a direct acyclic graph with temporally disjoint paths. Okay. So these are the two problems that we will be talking about now. And we asked that for which class of temporal DAGs have the Dilworth property. Okay, so that is the combinatorial aspect. And of course, the computational complexities of these two problems is also in our interest. And here is a summary of our result. So let's if your the temporal DAG is oriented paths or rooted trees, then you can solve both this temporal path cover and temporally disjoint path cover in polynomial time. Yeah, these are not so difficult to do, but when it comes to oriented trees,
can someone who's not Dibyayan confirm whether this is us or Dibyayan?
It's also frozen for me.
It's frozen for me also.
Okay, thanks.
Am I audible now?
Yeah, sorry, we lost you for a moment there. The last thing you said was that oriented paths and rooted trees are not so difficult. And then you went,
Exactly like that, yes.
Yes.
But it's not that.
Am I audible now?
Yes.
Sorry.
Okay. No worries.
So yeah, what I was saying is that if you have oriented paths or rooted trees, these two problems are polynomial time solvable. But for oriented trees, the temporal path cover is polynomial time solvable, but the temporally disjoint path cover becomes NP hard. And for general directed acyclic graphs, both these problems become hard, but we have some FPT or XP results. Now, what we noted was that whenever we had a polynomial time algorithm, we also had the Dilworth property for that class of DAGs. Now, I'm not saying that there will be any Fanon leaf connection between them, but it's a thing that we noticed. So, as I said, I will mostly focus on our algorithm for oriented trees. Okay, and so this is what I'm going to present now. And the idea of the whole algorithm is quite simple. Okay, so we construct the connectivity graph. So that is it is a graph on the same set of vertices of the tree, where two vertices are adjacent if they are temporally connected in the tree. Okay. So that's the first step of our algorithm. The second step is to compute a minimum click cover in the connectivity graph. Okay. And as it turns out, the minimum click cover gives a minimum path cover of the tree. Now, why? So we have to show that this whole algorithm is polynomial. And of course, the first step is easy. Now, the second step, we have to show that the connectivity graph is structured enough so that you can compute the minimum click cover. Okay, and that's what the bulk of the effort that goes into. And then we also have to prove this lemma, which would say that, okay, every click in the connectivity graph indeed corresponds to a path, a valid temporal path in the tree. So, yeah. So why? So just to have some idea about why this could be true. So let's say you have a click in the connectivity graph. Now it's a tree, so this edge represents either a path from, let's say, U to V or V to U, but not both, right? Because it's a tree. So you have a good orientation of the click, and also if you have an arc from U to V and V to W, now the only way there can be a path between U and W if there is actually a path that starts at U and goes to W. So what you have in the end is that if you also put these arcs on the connectivity graph, then every click becomes a transitive tournament. Okay. Now this is kind of at every step we are using, and that the fact that it's a tree, the underlying graph is an oriented tree. So in this way, you can say that for every click in the connectivity graph, I can find a temporal path in the tree that contains all the vertices. Okay. So this so that would mean that a click cover in the connectivity graph gives a temporal path cover in the tree. So now the second step is to show that the connectivity graph is actually structured enough so that you can compute this minimum click cover. Yeah. And what we end up showing is that this connectivity graph is a perfect graph. Okay, it's a subclass of a perfect graph, which is known as weakly caudal graphs. So, and again, once we show this, we have the Dibyayan property, right? Because in a perfect graph, the size of the minimum click cover equals the size of the maximum independent set. Now, maximum independent set in the connectivity graph actually gives a maximum anti-chain set in the temporal tree. So we also have the Dibyayan property here. So I will give you a very brief proof sketch of how we show it's a weakly caudal graph. First, we show that there are no holes greater than 4 in the connectivity graph. Okay, it would have been wonderful if the connectivity graph was caudal, right? But that's not the case. You can have holes, but the holes are not bigger. That's what we show. So to show this, the first we observe that if you have the vertices, if you do have a hole in the connectivity graph, then the holes are actually leaves of a connected subtree of the original temporal tree. Okay. Then once you show this, then the next step is to show that if you have so all these are actually the vertices of the holes. Yeah. So now if you have it's a temporal oriented tree. So either you have a arc going out. If you have an arc going out from this red, then for its neighbors, the arcs should be incoming, right? So there is an alternation between in arcs and out arcs from and to this subtree T prime. Now this immediately says that you cannot have a odd hole in the connectivity graph. And with some more effort, one can show that there is no even hole in the connectivity graph as well. That requires some case analysis, but the idea remains the same. Now the next step is to show that there are no anti-holes in the connectivity graph. So what are anti-holes? It is complement. So anti-holes are basically complement of holes of length greater or equal to 5. Yeah. So that's what we call anti-holes. Now, because of the previous lemma, we already know that you cannot have an anti-hole of order 5 because complement of a 5 cycle is again a 5 cycle. So you cannot have that. But with some effort, we can show that you do not have anti-holes. And how do we show that? Is that suppose you do have a large anti-hole, then you find these cliques, yeah? Find this, let's say the green clique and the red clique of the vertices with odd parities. If you number the vertices of the anti-hole, then you have the odd and the even vertices. Based on that, you can get these two cliques. Of course, there is this issue of whether the anti-hole is of order of the parity of the holes, but we can handle that. But anyway, you have these two cliques. Now these two cliques now corresponds to two paths in the original tree. Then based on how these two paths behave, we can distinguish with two cases. And in each case, so let's take the first case where the two paths don't intersect. Okay, then let's take the last vertex of the green clique. Yeah. Now it does not see only the two red vertices which are neighbors, which are just before or after it. So what you must have is this scenario. Yeah. So what you must have is that these two vertices are the last two vertices of this. Yeah. Now we don't really have any other way to put these green vertices, the rest of the green vertices. So a temporal path of this edge cannot exist. We can always show this. Now, the other case is that these two paths intersect. Then again, with a slightly different arguments, you can show that that this cannot happen again. But this is how we distinguish the cases. Yeah. So, as I said, the connectivity graph is hole and anti-hole free of size more than 4. which says that it is weakly caudal, which is a subclass of perfect graph. And it also means that we have the Dilbert property, as I said earlier. And yeah, we have that. So as I said, the connectivity graph is not caudal. So you cannot really strengthen this further. Of course, it's not true that all weakly caudal graph can be realized as a connectivity graph of some temporal oriented tree. I'm not sure about it, but yeah, we cannot get we cannot show that, we cannot hope for caudality in the connectivity graph. So along with these hardness results, I will quickly go through some of the hardness results that we have. So temporal path cover is NP hard on temporal directed acyclic graphs, and it's a reduction from three-dimensional matching inspired from Monod and Toulouse, which is used to show this kind of. So it's a standard trick that has been also used earlier. But the point to note here is that in our reduction, the number of time steps is 2, which is small, but the tree width is the tree width of the underlying constructed graph can be large. So, and also what we show that the temporal disjoint path cover is NP hard on temporal oriented trees, and the reduction is inspired is from Inari bin packing, and it's inspired from Poons, Mota, and Zahavi. Now here we have the tree width is 1, but the number of time steps is unbounded. Yeah, and it, of course, again, we don't have the temporal Dilbert property for this class of graphs as well when we talk about temporal disjoint path cover. So now what we look for is parameterized complexity of temporal path cover and disjoint path cover. And we show that temporal disjoint path cover is fixed parameter tractable with respect to the tree width and also the total number of time steps. It's a standard dynamic programming which is based on these 2 observations. I will not go into more details, but it's basically we guess everything because it's a partition. Because the temporal paths that we want has to be disjoint, temporally disjoint, then it becomes an FPT actually, and you do a standard dynamic programming on the tree decomposition. So, yeah, I will not go into the details of this, but we cannot apply the same thing for temporal path cover because in temporal path cover the paths can intersect, yeah, and therefore we could not manage to get an FPT algorithm, but what we get from the dynamic programming is an FP algorithm. So that is kind of, I would say, an open problem. So, yeah. So can we get a better FPT algorithm for, so what are the open problems now? So can we get a better FPT algorithm, or can we get, can we get approximation algorithms? And also what is interesting to me is like for which oriented trees or for which class of temporal DAGs this temporal Dilbert property holds. A nice characterization would be interesting. Thank you.
Thank you very much, Dibyayan. Any questions first from people in the in the Zoom? No, very good.
Yeah, so you either explore just path cover or disjoint paths. Have you considered an intermediate thing where every node has some capacity up to how many paths can be intersecting at any given time step, and work on that? I mean, the negative results carry pretty much, but I'm curious about the positive. Whether you have thought about it, or you can talk about it.
Well, we have not really thought about it, and the fact and the reason that we have not thought about it, because apart from this FPT result that we get from the dynamic programming, let's take the temporal oriented trees, for example, and try to solve the temporal disjoint path cover. Even here, we don't know whether we know that it's NP hard, but even getting an approximation of some sorts seems difficult. So temporal disjoint path cover, we don't know. I mean, we don't understand it well, even to go to that thing where you have this kind of extra necessity, where you allow this extra freedom of disjoint. But yeah, we don't know. We don't know much about it.
Okay, thank you.
But it's of course an interesting question. Yeah.
Any other questions? No. So maybe I might have been in the talk already. I might have missed it. So you showed that for temporal path cover, Dilworth is a sufficient condition, right? If you have the Dilworth property, then you have temporal path cover, right? Did I understand that correctly, or I just got confused?
So for temporal oriented trees, what we show is that the minimum temporal path cover, the cardinality, is same as the maximum anti-chain set. But of course, the size of the largest anti-chain set is a lower bound on any temporal path cover of any DAG. But in general DAGs, you don't have this equality. Actually, the gap between the maximum anti-chain size and the required number of paths can be very high. In general directed acyclic graphs.
Okay. Okay, if there are no more questions, I think we're at time anyway. Thank you very much, Dibyayan.
Yeah, thank you.